Okay, good morning. In today's session, I will be discussing about the temperature stresses in composite sections. So, composite sections means consisting of two different materials, two or more different materials. Structural element made up of two or more different elements. Okay, when a single material is there, then we have seen already how the temperature effects cause stresses in the material when the free expansion is restrained. Free expansion, when it is restrained, then you will have additional stresses developed in the material of the body. So when the member is made up of two or more different materials, then how it behaves? Because the different materials behave differently because of their linear expansions, different linear expansion, different coefficients. Okay, so the behavior will be different for different materials. When they are free, then there will be no stresses as such. Okay, when they are fixed, when they are rigidly fixed, when two different materials are rigidly fixed, then because of their different behavior and temperature rise, the differential stresses will be developed in the materials. Okay, so let us see the case of two different materials. Okay, a member made up of two different materials, when subjected to temperature rise, okay, what happens? When they are not connected, they expand freely, there is no problem. Okay, and no stresses will be developed. The expansions will be different for different materials. For example, there is material 1 and material 2. The initial length be same for both. Initial length is same. So, under the rise of same temperature T degrees, one material expands by delta 1, the other material expands by delta 2 because of their different coefficients of expansion. Okay, thermal expansion. The material, one material may expand more, one may expand less. Okay, that is based on their coefficients of linear expansion. Okay, when they are free to expand, this will be the case. They expand by different amounts, delta 1 and delta 2, and no stresses will be developed because they are free to expand. But when these two materials are rigidly fixed, then what happens? So, when two materials are rigidly fixed, let us suppose one material is steel, one material is brass. Okay, when they are free to expand, they will expand by different amounts, delta 1 and delta 2. This is delta 1 and this is delta 2. Okay, but when they are connected firmly, rigidly, what happens? Actually, brass expands more. And steel expands less comparatively. As they are rigidly fixed, what happens? They expand freely up to delta 2. The coefficient, the expansion of steel, because up to that there will be no problem. They both expand up to delta 2. Beyond that, what happens? Beyond delta 2, what happens is, because the materials are rigidly fixed, this is brass and this is steel. Brass, for the expansion of T degrees centigrade we are talking about. Okay. So brass expands by delta 1, which is greater than delta 2. So it still has the tendency to expand. Brass still has the tendency to expand beyond delta 2. Beyond delta 2. Because its expansion is delta 1. Free expansion is delta 1 under the rise of temperature by T degrees, isn't it? So it has the tendency to expand more, which is prevented by steel bar, because it is connected to steel bar rigidly. Steel bar prevents it from expanding by delta 1. Okay. And also the steel bar, if it is free to expand, it stops expanding at delta 2. But as it is connected rigidly to brass, it will have the tendency, as brass has the tendency to expand, it exerts a tensile force on steel. It exerts a tensile force on steel and it makes it expand beyond delta 2 also. Beyond delta 2 by some amount. Okay. And at the same time, it will not expand by up to delta 1 from initial position. It will stop at some additional expansion of delta. Okay. Because steel prevents it from expanding to its full length, delta, full expansion, delta 1. Okay. And also brass will make steel bar to expand beyond its free expansion, delta 2. Okay. That means the final expansion will be between delta 1 and delta 2. The final expansion of the bar will be between, if this is the initial length, then the final expansion, initial length L, final expansion is delta, then delta will be greater than delta 2 and less than delta 1. This will be the case, due to which the steel bar will be subjected to tension and brass bar will be subjected to compression. Okay. And it is how much stress will be developed now because of this in both the materials. Okay. How much stress will be developed in the materials when connected rigidly. Okay. So here, in this case, if you consider this case, the final expansion delta, now the steel bar will be under a tensile force and brass bar will be under a compressive force. These forces will be the same. These forces will be the same. Okay. So what is force P now? If sigma 1 is the force stress in brass bar, sigma 2 is the stress in steel bar, then P is given as sigma 1 A1. That is the cross sectional area of brass bar. Similarly, P is given as sigma 2 A2. So sigma 1 A1 will be equal to sigma 2 A2. This is the condition. Okay. To solve these stresses, sigma 1 and sigma 2, we will make use of these conditions. Okay. Also, let us see this case. Sigma 1 is stress in brass, and let epsilon 1 be the strain in brass. Okay, alpha 1 is coefficient of linear expansion, A1 is cross sectional area for brass bar, and sigma 2, epsilon 2, alpha 2 and A2 corresponding values for steel bar. And let epsilon be the actual strain of the composite bar per unit length. Okay. So just now we have seen the condition sigma 1 A1, that is force P. This is equal to force P to which the materials are subjected. Okay. One is subjected to compressive force P, the other one is subjected to tensile force P. Okay. Equal and opposite forces. So sigma 1 A1 will be equal to sigma 2 A2. Okay. Now, what is the strain in brass bar? Strain in brass bar is, for example, what is the free expansion of brass beyond its initial length L? This is brass bar, say. Beyond its initial length L, it expands freely by alpha TL. Okay. So what will be the strain? Strain is expansion by length, alpha 1 T. Alpha 1 T. But it settles at delta. It settles at an expansion of delta. The final expansion is only delta because it is not free to expand, connected rigidly to steel bar, isn't it? Final expansion will be less than that of free expansion, alpha 1 TL. Okay. And this is the compressive strain to which brass bar is subjected to because of this force P. Because of this force P or stress sigma 1 developed, it is subjected to a compressive strain of epsilon 1. Here epsilon will be the final strain. Okay. Beyond the initial length, it expands by delta. So the final strain of brass bar is epsilon. Okay, actual strain of brass bar is epsilon. Actual strain is epsilon. So what is the compressive strain now? Due to the stress P, the brass bar is subjected. It is epsilon 1, which is equal to alpha 1 T minus epsilon. Alpha 1 T minus epsilon. That is what is given here. So strain in brass bar is alpha 1 T minus epsilon. And strain in steel bar. What is strain in steel bar? Yeah, beyond its initial length, it expands by alpha 2 TL if it is free to expand. But because of the rigid connectivity between brass and steel, it still expands beyond this free expansion to a length delta beyond initial length. Okay. So the final strain of steel bar is also epsilon and its free expansion is alpha 2 TL. That means strain is alpha 2 T. So what will be the strain to which it is subjected because of the tensile force P acting on it? So this is the strain beyond free expansion. Alpha epsilon 2 is the strain beyond free expansion to which it is subjected due to the stress developed in the steel bar. Okay, because of the rigid connectivity between the steel and brass bars. Okay, that means due to this force P, it will be elongated by some amount beyond the free expansion. and the corresponding strain is epsilon 2, which is given as epsilon minus alpha 2t. Epsilon minus alpha 2t. Okay. So, what is the sum of these two now? Adding these two, you will get epsilon 1 plus epsilon 2. Epsilon 1 plus epsilon 2 is equal to these two gets cancelled. So, we'll have t into alpha 1 minus alpha 2. T into alpha 1 minus alpha 2. Also, epsilon 1 is p by sigma 1 and epsilon 2 is p by sigma 2. So, the force, sorry, it is not P. Just right. Sigma 1 by G. Sigma 1 by G. And this is sigma 2 by G. Okay. Epsilon 1 is sigma 1 by E. Epsilon 2 is sigma 2 by E. Okay. So, substituting these values, we can find the stresses sigma 1 and sigma 2. Sigma 1 and sigma 2. Because we know one relation between sigma 1 and sigma 2. The second relation between sigma 1 and sigma 2 is obtained here. Okay. So, we can solve for sigma 1 and sigma 2. Okay. Now, let us see some numerical examples. Okay. Consider this. A flat steel bar 200 mm by 20 mm by 8 mm is placed between the aluminum bars of same length 200 mm, same width 20 mm and thickness 6 mm so as to form a composite bar as shown in the figure. So this is the composite bar. This is aluminum plate. This is one aluminum plate and steel plate is placed between these two aluminum plates. Okay. So what is the areas of these two? Area of steel bar is 20 by 8 and area of aluminum bar, this is area of steel. Area of aluminum bar is 20 by 6 and 20 by 6 because these two we have 20 by 6 and 20 by 6. So 2 into 20 by 6. Okay, 2 into 20 into 6, that is cross sectional area of steel. And Young's modulus of steel is 200 gigapascals, that of aluminum 80 gigapascals, and temperature rise is 50 degrees centigrade. Coefficients of expansion are 12 into 10 power minus 6 per degree centigrade for steel, 24 into 10 power minus 6 per degree centigrade for aluminum. Okay, so this is the data given. So how to find now the stresses sigma 1 and sigma 2? Yeah, these are rigidly connected now. Okay, that means what relation we use? The force in steel bar is equal to force in aluminum bar. The tensile force in steel bar is equal to compressive force in aluminum bars. It means the aluminum bar is subjected to compression and steel bar is subjected to tension. Okay, the reason we have discussed already. Okay, because of high coefficient of linear expansion, thermal expansion, aluminum tends to elongate more, causing steel bar to be subjected to tension. At the same time, it is subjected to compression. because it is restrained from free expansion, complete free expansion by steel bar. So there will be compressive force in aluminum bar and tensile force in steel bar. Okay. Yeah. So the areas are, for steel it is 20 into 8, for aluminum 2 into 20 into 6, 160 and 240 mm square. And the condition that we have seen already, the tensile force in steel bar is equal to sigma s as, and compressive force in aluminum bar is sigma a suffix e, area of aluminum. Okay, that is equal to P. Okay. From this you will get relation between stress in steel and stress in aluminum bar. So area of aluminum is 240 and that of steel is 160. So 240 by 160, that is 1.5. Stress in steel is 1.5 times stress in aluminum. Okay. So this is one relation we have between these two stresses. Also, stress in steel is strain in steel is stress by Young's modulus, stress sigma s, and Young's modulus 200 into 10 power 3 Newton per mm square. Similarly, strain in aluminum is sigma a by Ea, stress in aluminum bar by Young's modulus of aluminum 80 into 10 power 3. Okay. Now we have another relation. What is it? Epsilon S plus epsilon A, strain in steel plus strain in concrete, is equal to T into alpha A minus alpha S, and epsilon S in terms of sigma stress we substitute. Okay, that means these two values we substitute here. So already we know sigma S is 1.5 times sigma A. Okay, here we have found one relation between these two. That relation we will substitute here. So on the right hand side, these are known values: temperature rise and coefficient of expansion. So the unknown sigma A can be found from this. Okay, that is 30 Newton per mm square, and sigma S, the corresponding stress in steel, is 45 Newton per mm square. Okay, is this clear? So that's how we'll find out the stresses in composite sections when rigidly connected and subjected to temperature rise. Okay. Another example we will see. A gunmetal rod of 20 mm dia, screwed at the ends, passes through a steel tube 25 mm and 30 mm internal and external diameters respectively. Here is a steel tube of external diameter 30 and internal diameter 25, and through which a gunmetal rod is passing, which is screwed at the ends. Okay, the nuts on the rod are screwed tightly home on the ends of the tube. Okay, that means they are rigidly fixed at the ends. Now they both are subjected to a temperature rise of 200 degree Fahrenheit. What will be the stress intensity in each of the materials? Okay, that you need to find. Coefficients of expansion are 6 into 10 power minus 6 per degree Fahrenheit for steel, 10 into 10 power minus 6 per degree Fahrenheit for gunmetal, and modulus of elasticity for steel is 200, that for gunmetal is 100 gigapascals. Okay, so this is the case, they are fixed tightly at the ends. Okay. That means when these are subjected combinedly to a temperature rise, what happens? They both tend to expand, but because of different coefficients of expansion, gunmetal tries to expand more and steel tube less. Okay. But as they are connected tightly at the end, they both expand by the same amount, delta, which causes a compressive force in gunmetal and tensile force in steel. Okay. So the reason is same as the previous problem. Okay. So we have the relation now, sigma SAS is equal to sigma G AG. That is equal to the compressive force in one and tensile force in the other. They both are equal in magnitude. Now areas are area of steel tube in terms of pi, 68.75 pi mm square, and that for gunmetal rod is 100 pi mm square. Okay. So now from this relation you will get sigma S in terms of sigma G, stress in steel, equal to 1.45 times stress in gunmetal rod. So this is one relation we got. Also, strain in steel is due to this stresses developed, sigma S by ES, and in gunmetal it's sigma G by EG, and substitute those values in this relation. Okay. And also replace sigma S by 1.45 times sigma G. Now from this you will get stress in gunmetal rod 46.4 Newton per mm square, and in steel 1.45 times of this 46.4, that is 67.3 Newton per mm square. Okay. Yeah. So like this we can solve the problems of composite sections when rigidly connected and subjected to temperature rise, temperature change. Okay. Yeah, that's all for this session. We discuss some more examples on this in the next video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.